This section is very interesting because it's gonna show us what's the relationship between differentials and integrals. What we have studied before was if we had a function f, then for every x we can actually find the slope of the tangent line, and all those values are going to form a new function that we called f prime. So what is the relationship between this derivative function, or being able to take the derivatives, with this new thing that we call integrals, which is finding the actual area under the curve of any function? So we're going to see what is the connection between them. This is a very important part of calculus. The name sounds like it, fundamental theorem of calculus, and it's going to be very exciting and actually illuminating. It's going to simplify a lot of the calculations that we've done so far, because as you may have seen, finding rectangles for every single function and making a lot of rectangles is very tedious. The fundamental theorem of calculus deals with two parts. And the first part deals with equations defined on the following way. I'm going to have a function that I'm going to call g of x. Remember that I could have chosen any other letter. Right now, let's just call it g. And then we're going to see what is a better name for this function. So this function is actually the integral for some number, fixed number a. So I have a function. I'm just going to make it positive right now, but you will see that how is true for functions that are negative. From some number that I pick a all the way to x, and since this is the function f, since this is the integral, that means I'm finding the area here up to x. So you can think of this function as the area so far up to x. Okay, so this function g is going to take several values as I'm moving x from a and on. In here, I don't know, maybe the g of x up to here is 4. If x is later on over here, then g of x may be 5. So as I'm accumulating more area as x moves on the right direction, then g of x is going to be a number that is going to be growing as well. So let's just see how the shape of g would be. So at the beginning, x starts at a, so the area under f of a single point is 0. And then as x is growing, the area under f up to x is growing. So I'll just g will be a increasing function as x moves along, and as long as f is positive, I'm just accumulating more area, and more area. So g of x is going to keep growing as x grows. So that's the idea. This is a very weird looking function because we've never seen a function in which the variable, the independent variable, is actually the upper limit of the integrand. But we're going to see how that makes sense. So as I said before, if f happens to be a positive function, then g of x is simply the area under the curve up to x. But you probably are wondering what happens when f is a negative function. Then we can't think of it as the area anymore, just in simple terms. It would be the sum of the signed areas. Remember that if f is negative, the area below the x-axis will be considered negative. So the g of x probably is going to stop growing, and it's going to start decreasing once you start adding negative areas. So in here everything is positive and the area keeps growing. Once you pass this point, you're adding negative numbers, therefore g of x will start decreasing at some point. And that's what will happen if f is a function that goes from positive to negative. So this is an example that is more elaborate than the one that I've given you before. It says if f is a function whose graph is shown and g is defined as the integral from 0 up to x of this function f. Remember that we could have called f of t or f of h, of f of c, of f of theta. We could have all these names as long as the term after reflected that variable. F of h, we could have used dh. F of z, then it would have been dz. F of theta, it would have been d theta afterwards. So in here, the independent variable is x, and it's on the upper limit of the integral. Okay, so since we're trying to find what would be the sketch of a function like this, we go to the most elementary way of graphing functions, table of values. So these are the x's, these are g of x, and I have 0, 1, 2, 3, and 4, because I'm trying to sketch the shape of a function that I really don't know how it behaves, and I really don't have an equation to plot. So table of values is the most elementary way of doing so. So let's find what g of 0 is. G of 0 is the integral from 0 to, since this is where the x goes, I have to put 0 here, of f of t dt. Now remember that this is the interpretation of an integral, the area under f, when f is positive. So if this is the area, sorry you can't see that, if this is the area under f, then I'm gonna find the actual area. If this is f, from 0 to 0, you notice that there is no area to speak of, so this is immediately 0. Now g of 1 is the integral between 0 to 1 of f of t dt. Again, the meaning, this is the area under f. So from 0 to 1, I want to know what this area is. Now, I don't need rectangles within this shape to know the area, because if I know area of triangles, then I know how to find the area of this function between 0 and 1. This is a triangle, so I just simply use the area formula for a triangle. I don't need to split it up in 6 or 8 rectangles. So area of a rectangle, half of base times height. So half of 1 is half, times 2 is 1. So this is simply 1. Now g of 2 will be the integral from 0 to 2 of f of t dt. Now on the previous section we learned the properties of integrals. If I'm trying to find the area between 0 and 2, I can just split it into the area from 0 to 1, because that's the one that I do know from the previous step. And I just have to add the area from 1 to 2 of f of t dt. So I know from 0 to 1 the area is 1, and now from 1 to 2 the area is a rectangle, so base times height would be 2. So this is worth 1, this is worth 2, 1 plus 2, 3. Who says that calculus is difficult? 1 plus 2, 3. Yay! Now g of 3. G of 3 is the integral between 0 to 3 of f of t dt. And now I can split this again. The area from 0 to 1 plus the area from 1 to 2 plus the area from 2 to 3. Or I could have said the area from 0 to 2, because that's what I know from the previous step. But it's okay. This was worth 1, this was worth 2. Now this one is new. So from 2 to 3 is this area, for which I do not have a formula for, because it's not half of this rectangle. You notice that half will be here. Okay, like this area will be the same as 1. I notice that it has like a little bump, and that's a little bit more than 1. So let's approximate it to 1.3. So 1 plus 2 plus 1.3 is 4.3. Now g of 4 it could be g of 3 plus the area from 3 to 4. From 3 to 4 f t dt. Or you can break it up into from 0 to 1, from to 2, from 2 to 3, and from 3 to 4, but you know how this is just a pattern, so I'm just going to use the last answer. So this will be 4.3 plus the new area. And the new area, again, this is something that I don't have a formula for. From 3 to 4 is this little bump. But since I approximated this one as 1.3, so then I'm going to approximate this one as 1.3. But because it's below the x-axis, it has to be negative 1.3. So 4.3 plus negative 1.3. And that gives me 3. Now g of 5, I didn't write it, but they are asking me for g of 5. Will be the previous one, which is 3, plus the area between 4 and 5. Since by symmetry this is negative 1.3, this is also negative 1.3. So the last answer plus the next area, and that would be about 1.7. Now the explanation for all this is step by step done in here, and it has accumulative areas, and if you didn't understand what I just said, you can go ahead and read those one by one. See, the area g of 3 is g of 2 plus the area between 2 and 3, so they are adding up, and even adding the negative areas as well. So you can follow that if you didn't get what I just said. Now, from our beautiful table of values, we do have some points about g. G of 0 is 0. G of 1 is 1. So that point is there. G of 2 is 3. And that's right there. G of 3 is 4.3. G of 4 is 3 again. And G of 5 is 1.7. So since we know that f is continuous, g is also going to be continuous, so it does make sense to connect all those points that we know from our table of values into a smooth shape. Now let's just see the reasonableness of things over here. G is a function that is increasing up to 3, reaches a local maximum, and then decreases. Why do you think the absolute maximum here, the local maximum here, I don't know if this is it for f, then this would be an absolute maximum. But why do you think we have a maximum at 3? Notice how all these areas are positive, and as I'm moving x along the x-axis up to here, all we've been doing is adding positive areas. Past this point, we're going to start adding some negative areas. Therefore, the sum will not be as highest anymore. So from 3 to 4, you see a decline on the area, the sum of the signed areas. So I have positive ones. As soon as I add some negative values, then the sum is not as highest anymore. So the highest point that I'm reaching is at 3. Now, doesn't that ring a bell or reminds you of when the derivative of a function was 0, when we were reaching a maximum or a minimum value? So these things are going to start to make sense in the future slides, but there is a very strong relationship between these integrals and derivatives. Now we need to slow down a little bit about this. It says if we take f of t as t and a equals 0, then we have this integral being worth this. So let's slow down a little bit. We don't know where this formula came from, so it is just related to a problem that we had in section 5.2, but I don't think it was assigned. So let's just retrace our steps a little bit. If I'm finding the area between a and b in general of f of x dx being f of x just simply x. So I have the y equals x line, or the function f of x equals x here, with important points 0, 0, 1, 1, 2, 2, and so on. Those are important points about this function. This is the identity function. So if I'm trying to find the area between any 2 points in general, a and b, so the area under the curve is going to be the area of this trapezoid, and I don't know if you agree with me. Of course you do. So the integral between a and b of x dx is, and we're going to have something in terms of a and b definitely. So the area of this trapezoid, remember that area of a trapezoid is the average of the bases times the height. In this case, the trapezoid is standing up. Right now it's laying down. So average of the 2 bases times the height. So the average of the 2 bases times the height. Now this base is as tall as, remember that this is the line y equals x, or f of x equals x. So if x is a, then b is a. And in here, if x is b, then y is b as well. So the bases are a and b. And now the height is b minus a. Is the difference between these two numbers. This is how long this space is. So the integral becomes, and I know that this rings a bell, the sum times the difference is just the difference of squares. So for any time I'm integrating between a number and another of, in particular, the function x. So in particular, if a is 0 and b takes the place of x, we can have 1/2 of x squared minus 0 squared, and this is simply x squared over 2. But now I don't want you to get lost in the ton of information that you've seen so far. Remember that the function g of x is defined as the integral between a and x of ft dt, and only when f of t is simply t, only when we're working with the identity function, only when we're working with this particular function, then this integral can be simplified to this expression. But that is not going to be the case with a different function. So just pay attention of that particular fact. So notice that if I take the derivative of g, obviously I can't take the derivative the way it's written in here, but I could take the derivative with the tools that we have so far. But I could take the derivative of g written this way, and the derivative in here would be 2x over 2, which is simply x. So what does this mean? It means that g prime of x is simply x, which is the way f was defined. So if g is defined as the integral up to x of f, then its derivative is going to be simply the original function. So what does this mean for our graph? It just means that the area so far, the function defined as the area so far, the change of rate on that function is simply the original function. So isn't that something? So let's go and study a little bit more on this on a general function. So now let us see how we are going to estimate the rate of change of our function g, being the area under the curve so far, or all the way up to x. Remember that rate of change is going to be not only the difference of the y's over x's, but the way G changes is going to be given by how much the area changes, because G is area. Since G is area, then I want to know what is the difference between the areas of between X and some small amount that we have seen how to deal with, X plus H. So let's see that the difference in the areas between X and X plus H is going to be given by the area of this very thing, almost a rectangle. But it's not quite a rectangle because you will be missing this little corner right here. So approximately the difference between the area up to X plus H minus the area up to X is about the area of this rectangle. The base will be H, and how tall is it? It is as tall as f of x. So if I divide both sides of this equation by h, I have f of x is about the difference of the areas over h. Now, if I take the limit as h approaches 0 of this, what I'll be finding is g prime of x, and g prime of x is the original function f of x. Isn't that beautiful? Here it goes, the first part of the fundamental theorem of calculus. Let's read the formal definition, and then we talk about what it actually means for us. So it says, part 1, if f is continuous, and this is very important piece, on a closed interval, then we're going to define a function g as the following. G of x is the area under the curve between a and x of some function. That's the function that has to be continuous, by the way. And we're going to make x change from a to b. And this function is continuous on the closed interval, and it's differentiable on the open interval. And the idea of having this area function is that its derivative is the original function. Now, I'm going to take this statement and I'm going to write it using Leibniz notation. Leibniz notation is the one that invented d over dx. So remember, g prime of x is just the same as d of gx over dx, right? And that is saying that it's the same as the function f of x. Since I'm defining g of x as this integral, then the derivative respect to x of the integral between a and x of some function is f of x. So let's just read this by chunks. The derivative of an integral of a function is the function itself. What? Again, the derivative of the integral of a function is the function itself. So what does that mean for the meaning of the integral and derivatives? It means that the processes are inverses. Taking the derivative and taking the integral are inverses. And this is very powerful because, roughly speaking, if we have the definition of part 1 of the fundamental theorem of calculus, we say if we find the integral of f and then we take the derivative of it, then we get the function f, or the original f. So if I have a function f and I'm integrating, okay, from a to x, since I'm integrating up to x, then I can't call this x, I have to call it t or some other function. So if I'm finding the integral of f, if I'm integrating f, and then I'm taking the derivative, what do you get? You get the original f. Awesome. Now, let's do example 2. and then you're going to see what this means. It says find the derivative of a function g of x. Notice how x is the independent variable and it's right here on the upper limit of the integral. I'm going to find the derivative of this function defined as the integral from 0 to x of this function. In this case, f of t is in particular square root of 1 plus t squared. Okay, so I'm finding the derivative. I'm finding g prime. Okay, ready? This is going to take a very, very short time. So if g is defined as this, the derivative, square root of 1 plus x squared. Done. What? Yes, exactly that. And this is because we are applying the fundamental theorem of calculus part 1, because that part says if we're defining a function in this manner, I know that the derivative will be the original function that I'm integrating, the integrand. The only thing here is that I can't say the derivative respect to x of g of x. I can't put in t. I have to be consistent with the variable c. So if I'm finding g prime of x, naturally the function is going to be in terms of x and not in terms of t. So that's it. We're just applying that part, and it's as simple as that. Does that work with other functions? Absolutely. So if g of x is defined as the integral from 0 to x of sine of pi t to the e k t plus let me see, t to the 5/3 cosine of t plus square root of t squared minus natural log of t minus 4 dt. Okay, so let's say that I'm trying to find the derivative of g prime of x. Do you know what that's going to be? That's going to be simply this entire function in terms of x. So it would be sine of pi x to the e k x plus x 5/3 cosine of x plus the square root of x squared plus natural log of x minus 4. Ta-da! That's it. So this is a very hard concept to understand, but in terms of computation, it is very simple. So it works as long as you know that f is continuous between 0 and x. So if f is continuous between 0 and x, closed interval, then definitely we can find something like this, and this is going to be that. So as long as this is true, then this is always going to be the correct answer for the derivative of g. So g looks complicated, but its derivative, very simple. So often in different areas like physics or biology or statistics, sometimes functions are defined in a very strange manner or not as easy to deal with, but their derivatives is something that is definitely more manageable. So help me out here. If s is defined as this integral up to x, notice how it appears on the upper limit of the integrand. The derivative I know is going to be the function itself evaluated at x. So this is a sinusoidal, and this is something that we already know how it behaves for any values of x. This one I'm not sure about the shape. So if I can study the derivative, I know enough of derivatives to figure out some properties about the function itself. And I know that you are thinking right now, you know, like, what do you mean? And for example, let me ask you this. If you know that derivative is 0, then what do you know about the function? And you're going to say, oh, okay, yeah, and it may have a minimum or a maximum depending on how the derivative changes before the 0 and after the 0. That is like, okay, see, don't you know something about this one? So in example 3, that is just to show you that particular point. This is the derivative, okay, the sine function that we just found right here. And the actual one, this function that has the integral in it, varies like this. So as you can see, the areas are positive up to this point. That's why S reaches a high point right here. And now S starts decreasing because as X moves along, we are adding some negative areas here. That's why the value is going down. And then it stops. When we stop adding negative areas, it stops right there, and we're going to start adding positive areas. So that's why the value from then on, it starts increasing again. So if S is the area function under F, the area under F, S prime is F. So if you have a function and you define the area under the curve as a function, the derivative of that area under the curve function is the function itself. Isn't that great? Okay, so let's just look at some features in here so that we know what is the relationship. Is F prime S or is S prime F? It can get a little bit confusing. So for example, right here, F has a 0. So because F has a 0, and you have S right here with a maximum, so you know that S prime is 0 when we have a maximum, and therefore F has a 0 right there. So I know that S prime is F and not the other way around. I promise I'll finish very soon. The second part is not as long as the first part. Let me just do example 4 to convince you that it is that simple. So if I'm defining this function, you can call it g of x, you can call it anything you want. But using the definition, if this is g of x integral between 1 to the x to the 4, some function f of t dt, then what I'm trying to find is the derivative. I'm trying to find g prime of x. And you know that g prime of x is simply f of x. So g prime of x here will be simply secant function. But now, what to do with the x to the 4 that you have here? So if I define this x to the 4 as some function, let's call it u. So I have g of u equals integral between u and 1 and u of secant of t dt. And you know that when we are taking the derivative of u, since this function is a function in itself, then it would be the derivative of this function times the derivative of u. So we know that we have to apply chain rule. So derivative of g would be the same as f of x, but it would be f of x evaluated at x to the 4th, and then I just have to multiply that by the derivative of x to the 4th, which is 4x cubed. So this will be 4x cubed times secant of x to the 4th, and that will be g prime of x. Now it is not as straightforward as before when we were able to compare the function in here with this, and the reason why this doesn't look like the inside of the integral anymore is because of this piece, and this piece came from taking the derivative of the upper limit of the integrand. This is just because it is not the integral from 1 to x simply, it's the integral from 1 to all the way to x to the fourth, and this is in itself a function, so you have to be careful. If it says the integral from 1 to x, then definitely your answer is going to match the function that you have inside. But right now it doesn't, and that's okay because I know chain rule.